Hey Coleman, I got the kitty litter you needed. How much did you say you needed again? About 6 inches. Huh. You know what? I think I can do that. So, when do you need it by? Oh, okay, that's pretty soon, but I think we can do that. Okay, see you later.
I'll see if I can make it happen. Optimization. Okay, so let's say we have a cat. Let's try to optimize a cat. Maybe put it inside of a box or something. So look it. We have our box. Good enough. And we're gonna try to fit a cat inside here. So we have a cat with a head that's a circle, ears that are triangles, a body that's maybe like a circle, oval. It has legs like that, and it has back legs too, and it has a tail. So let's just draw that as rectangles, I guess. So rectangle right here, rectangle right here, and a rectangle right here. There, we have a cat. Let's draw a little face on it.
Yeah. What's your idea of maximizing the cat inside the box?
So, if we could just, like I did, break up the cat into different shapes, we can maximize not each shape, or we could maximize each shape into the box.
So we add up all the areas and then maximize it to that?
Yeah.
So like breaking up each individual part. So for the example, all the paws should be around the same proportional. So it'd be area equals 4 pi r, since r squared, since they're all 4 circles. And then we have 2 similar legs, which are the back legs, are longer. So can we, what are they, like, say in rectangles? Or
Yeah, we could just say rectangles instead of...
yeah, okay.
Rectangles probably work better.
So if we have 2 rectangles, same size, the 2 legs, area of the legs, big legs, see that, equals 2BL. Right, since we have 2 areas, then area of the small legs equals 2B, not B, let's say XA, because they're different heights. Now, now we have the body, which is area equals pi r squared. Area of the circle, pi r squared. These 2 ears, area, the triangles to triangles, so it'd be base times height. And we have, what, right, another rectangle? I mean, yeah, rectangle, base times height. Area equals base times height. Alright, looks good.
And so once we maximize the cat, we're just going to put it back into this box. So I think that should work.
That should work, yeah.
Wait! If you notice here, the body of the cat and the head have to stay proportional. You can't have a cat that his head is bigger than his body, you know? So you can't just maximize it by parts. It all has to grow proportionally.
Oh crap, he's right. We can't do this. Do you have any other ideas?
Coleman asked that she wanted some cat litter. We have a machine that dispenses a solid volume, you know, inches cubed.
Mm-hmm.
So we can use that volume and but find the related rate at a certain height that she's asking for. So
Sounds perfect. I'll call Shanna later today.
okay, sounds good. We're going to be given a machine that is pumping sand into this cylinder tube. Well, it's connected to the cylinder tube. And the rate that comes out from the end of the cylinder tube will be 9.425 inches cubed. Our question is to find out how long it will take the sand to reach 6 inches in height of the box.
problem, we are given the box height, which is 10 inches, the box width, which is 18.5 inches, the box length, which is 24.5 inches, and the cylinder volume, which is 9.425 inches cubed. We're also given the rate at which the box is being filled up with sand, which is 9.425 inches cubed per second.
So now we go to setting up the problem. We know that the volume of the box equals length times width times height. So knowing this, we take the derivative of this equation with respect to t, which equals time. When we do that, we get dv dt equals length times width times the rate of height.
After we're given the equation, basically we just plug in all the values, which is the rate, the length, the width, and we solve for dHdt. And after plugging in all the values, we come up with dHdt is equal to 0.021 inches per second.
So on step 4, which is our last step, we're gonna find the time that it takes for the height to reach 6. We got this very final equation, which is height is equal to the rate at which the height is increasing times time. So now we just solve for time. Time is equal to h divided by the change in the height through time, and that is equal to and height is equal to 6, and the change in height through time is 0.021 inches per second. So after dividing that out, we get our time, which is 285.7 seconds.
All right, so the way this product works is the machine's going to be connected to this kind of cylinder type of pole, and the sand's going to be drawn out through the bottom of this. So it's going to go in, and it's going to be coming out at a rate of 9.425. Damn, what do we do now? All of our sand is just going to come out. Okay, so as you guys can see, Isaac made a hole in our box. So now we calculated that the rate of the sand that's coming out of the box is 2.45 inches cubed per second. So now what we're trying to find is the time it takes for all the sand to be released out of the box. Got it. Take that out. Boom.
Okay, so in this problem, the rate is given at 2.45 inches cubed per second, and the box width is 18.25 inches, and the box length is 24.25 inches.
Alright, so from the given, we can come up with the equation, which is volume equals width times length times height. And from there, we take the derivative of volume with respect to t, with respect to t, which is time, which is equal to the width times length times dh over dt.
So we're on the last step, and we come back to our equation. Distance equals the rate times time. In this case, the rate is actually the change in the height through time times time, because that's what the rate represents here.
You good?
Okay. You didn't really fit in the camera though.
Hey, boss.
So you wanna be a gangster. All that.
Good?
Yeah.
Okay, so now we go to setting up the problem. We know that the volume of the... We gotta do this again. We gotta
Okay.
do this again.
Yeah. Just keep going. I'll edit it.
Oh
I'll
my-
cut the thing. You don't have to.
You really wouldn't just like stop it? Okay.
It makes no sense to. Yeah, we can make bloopers and.
Let's do an optimization problem. Optimization.
It's called optimization.
I did?